Hello everyone, this is Dr. K. Evangeline Supriya, working as an Associate Professor of Physics, Department of Humanities and Science, SRIT Engineering College, Anantapur, Andhra Pradesh. Today I am going to give you a video lecture on Engineering Physics, Unit number 3, Dielectric and Magnetic Materials. So firstly we will study about the magnetic properties of materials. So we should know some basic terminology in magnetic materials. First one is magnetic dipole moment or magnetic moment. It is defined as the product of pole strength m and the distance between dipoles. Mu m is equals to I into A. The units for the magnetic dipole moment is ampere per meter square. Magnetic induction or magnetic flux density, which is denoted by capital B, and it is defined as the number of lines of force passing through the unit area perpendicularly. Units are Weber per meter square or Tesla. Magnetic flux. Magnetic flux is the product of average magnetic field times the perpendicular area that it penetrates. As you can see here, we have magnetic flux is equals to B into A. For a closed surface, you can see the sum of the magnetic flux is always equals to 0, which is Gauss law for magnetism. And magnetic induction or magnetic flux density. Magnetic susceptibility. So magnetic susceptibility is denoted by chi. It is the degree of magnetization of material in response to an applied magnetic field. M is equals to psi into H. Intensity of magnetization is denoted by capital M. When a material is magnetized, it develops a net magnetic moment. The magnetic moment per unit area, per unit volume is nothing but intensity of magnetization, units ampere per meter inverse. Permeability. This is the characteristic property of a medium. It indicates it is a measure of the ability of a material to support the formation of the magnetic field within itself. Mu is it is denoted by mu. Mu is product of mu r into mu naught, where mu r is the relative permeability of the medium and mu naught is the relative permeability in the space or vacuum, which is 4 pi into 10 to the power of minus 7 Henry per meter. And we can see the relation here, magnetic induction and magnetic field intensity are related by B is equals to mu naught into H plus M, where we will get, after deriving mu is equals to mu r into mu naught, we have to substitute here and we will get mu r is equals to 1 plus psi, which is the relation between relative permeability. Origin of magnetic moment. This is the first topic in this unit. Origin of magnetic moment. Orbital motion of electrons is nothing but orbital magnetic moment is the fundamental unit of magnetic moment, which is known as Bohr magneton, and mu b is equals to ELH by 4 pi m, which is equivalent to 9.27 into 10 to the power of minus 24 ampere per meter square. This is spin magnetic moment. Mu spin is equals to G into E by 2 MA into S, where G is the dimensionless numbers. It is also known as G factor. The number of this number depends upon the particle. For electron, it is equivalent to 2. Mu s is equals to 9 into 10 to the power of minus 24 ampere meter square. This is the spin motion of nucleus. Spin magnetic moment, which is denoted by mu n is equals to E by 2 MP into S. Mu n is equals to 5.05 into 10 to the power of minus 27 ampere meter square. Now the magnetic materials are classified into 5 groups. Depending on the alignment of dipole moment, the magnetic materials are divided into 5 types. They are dia, para, ferro, antiferro and ferrimagnetic materials. So first of all, we will study about the diamagnetism. Diamagnetism characterizes the substances that have only one magnetic atoms, that is lack of permanent dipole moment, and an electron moving around the nucleus results in magnetic moment. So the net magnetic moment is 0 in diamagnetic materials. The magnetization induced by the applied magnetic field is very weak. When an external field is applied, the motion of electrons in their orbit changes, resulting in induced magnetic moment. As you can see, these are the characteristics. Magnetic susceptibility is small and negative. Temperature dependence is independent, and examples are copper, silver and gold. This is a paramagnet. The paramagnetic substances consists of magnetic atom that possesses permanent dipole moment. Each electron in an orbital magnetic moment, it has a spin magnetic moment. In the absence of external field, the net moments of the atoms are arranged in random directions because of thermal fluctuations. Hence, there is no magnetization. When external magnetic field is applied, there is tendency for the dipoles to align with the field, giving rise to an induced positive dipole moment. You can see here, these are the characteristics. We can see magnetic susceptibility. Magnitude of susceptibility is nothing but small and positive, and temperature dependent psi is equals to C by T. Examples are lithium, tantalum and magnesium. This is a ferromagnetism. It is having the special property which is known as spontaneous magnetization. Even in the absence of external applied field, some substances exhibits a strong magnetization, which is known as a spontaneous magnetization. This is the special property of ferromagnetic materials. For this reason, only for the VH curve, the ferromagnetic material is chosen as a specimen because of its special property, spontaneous magnetization. So these are the properties. For the magnitude of susceptibility is very large and positive, and temperature dependent psi is equals to C by P minus theta F, where theta F is the Curie's law. For if for theta is greater than T is greater than theta F, it is the paramagnetic behavior. T is less than theta F, it is a ferromagnetic behavior. The examples included for the ferromagnetic material are ferrous, cobalt, nickel and galladonium. These are the few examples for the ferromagnetic materials. And you can see here, B in is equals to B out, which is a normal material. Suppose if B in is less than B out, it is a diamagnetic material. B in is greater than B out, it is a paramagnetic material. B in is greater than double greater than B out is nothing but the ferromagnetic material. Next one is, last one is antiferromagnetic material. This antiferromagnetism macroscopically similar to the paramagnetism, is a weak form of magnetism. Even in the certain materials, when the distance between the interacting atoms is small, the exchange forces produces a tendency of antiparallel alignment of electron spins of neighboring atoms. These are the characteristics. Magnitude of susceptibility is small and positive. Spins are aligned antiparallel. Temperature dependence chi is equals to C by T plus theta when T is greater than Tn, and psi is directly proportional to T capital T when T is less than Tn. These are the examples. The examples of the antiferromagnetic materials are salts of transition materials. Next one is ferrimagnetism. This is a special case of antiferromagnetism. The net magnetization of magnetic sublattices is not zero, since antiparallel moments are of different magnitudes. Hence, ferrimagnetic materials possesses a net magnetic moment. Above TC, thermal energy randomize the individual magnetic moments and the material becomes paramagnetic. You can see here the magnitude of susceptibility is very large and positive, and the temperature dependence I is equals to C by T plus or minus theta n when theta T is greater than Tn. You can see as a spin alignment or antiparallel of different magnitudes. Examples includes are ferrites. So these are the properties of 5 types of magnetic materials we have enlisted here in the table. You can see dia, para, ferro, antiferro and ferri. These are the characteristics features we have included. Number of electrons, what about the permanent dipole moment, origin of magnetic moment, spin alignment, effect of magnet, effect of temperature, permeability, susceptibility and examples. If you look at the table here, for the dia we have included all the examples, all the characteristics when it comes to the para, ferro, antiferro and ferri. You can see here the effect of temperature, how the susceptibility is varies with the temperature. We have included the formula also. These are the spin alignment. We have included the figures here, how the alignment of spins are there. In the para it is randomly oriented so that the resultant momentum is zero, and in the ferro it is parallel, and in the antiferro it is antiparallel, and ferri it is antiparallel with unequal magnitude. This is how we can differentiate the magnetic types of materials, or 5 types: dia, para, ferro, antiferro and ferri. Next concept is domain concept of ferromagnetism. We proposed this concept of domains in 1907. What exactly means of domain means a region in the ferro or antiferromagnetic material where all the magnetic moments are aligned in the same direction is called as a domain. Ferromagnetic material is divided up into these small regions called domains, each of which is at all times completely magnetized. This is a magnetic domain, single momentum. Further, this theory, this theory concept of domain concept of ferromagnetism explained is, if a magnet is broken into two pieces, each piece will be a magnet with north pole and south pole. A magnet is heated or roughly handled tend, tends to lose its magnetism. A specimen when magnetism suddenly experiences a slight change in its length, which is due to rearrangement of domain inside. This is called the magnetorestriction. There are two possible ways to align a random domain structure by applying a external field, where H is equals to 0 by the motion of domain walls, and you can see in the figure number 2 by the rotation of domains. To study the domain structure clearly, we must know the four types of energies involved. One is exchange energy and another one is anisotropy energy and domain wall energy or the block wall energy or magnetorestriction energy. First one is exchange energy. It is also known as magnetic energy. It is the energy required to assembling the atomic magnets into a single domain. Anisotropic energy, the excess energy required to magnetize a specimen in a particular direction over that required to magnetize it into the easy direction is called the crystalline anisotropy energy. Third one is domain wall energy, a thin region that separates adjacent domains magnetized in different direction is known as block wall or domain wall. Fourth one is magnetorestriction energy, the energy required to change in dimension of material which when it is magnetized is known as magnetorestriction energy. Next one is hysteresis curve. So the meaning of hysteresis is nothing but lagging. So what exactly lagging means? Hysteresis is characterized as a lag of magnetic flux density behind the magnetic field strength. The lagging of B, that is nothing but magnetic flux density behind H, which is nothing but magnetic field strength, is nothing but hysteresis. The lagging of B behind H is nothing but hysteresis. This is the curve we have got when we plotted against H and B. You can see this is the hysteresis curve. So when a magnetic field is applied to ferromagnetic materials, as I already told, because why we have chosen the ferromagnetic material means it is having the special property of spontaneous magnetization. Even in the absence of external field, some materials exhibits a strong magnetic field is nothing but spontaneous magnetization. This spontaneous magnetization exhibits only in ferromagnetic materials. That is the reason we have chosen the ferromagnetic material as a specimen in BH curve. When magnetic field is applied to ferromagnetic materials, they get magnetized and exhibits hysteresis behavior. Consider a ferromaterial placed in an external field. Let the initial point be 0. If the applied field strength H is increased, then the magnetic induction also increases from the point B, but the increment will be non-linear and reaches to P. Further increase in H will not show, hence P is called the saturation point. So this is called the P. From 0 it will goes on to P, and that it cannot increase. That is nothing but saturation. If H is decreased from this point, then it follows a different path. As you can see, from P it is following a different path. From the initial path at point Q, H will be 0. It is observed that H is equals to 0 induction. B has some values, B is equals to 0. This happens due to the lagging of B behind with respect to H. As I already told, hysteresis is nothing but the lagging of B behind H. This is because material got magnetized due to H, and the material retains its magnetism in H is equals to 0, which is known as magnetic retentivity or remanence magnetism. That can be denoted by BR. Thus, retentivity is defined as the amount of magnetization remaining in the material when the magnetizing force is removed. So you can see the coercive force is defined as the amount of force required to demagnetize the material or to destroy the remnants magnetism. Now that is how if this decreased from S, it will follows the path. You can see here it will from R it is decreased to S, again it will goes from S to T and U and then P. That is how the hysteresis curve is formed when graph is plotted against H and B. So that this is a cyclic process. From this analysis, it is observed that the magnetic flux density B is lagging behind magnetizing force H. Such behavior is known as hysteresis behavior, and the area which is under the curve, you can see this is the area under the curve, is nothing but energy loss, which is known as hysteresis loss. You can see here this is the curve behind the area, this is nothing but energy loss. Next one is hard and types of magnetic materials, hard and soft magnetic materials. You can see here hard magnetic materials are those which are characterized by large hysteresis loop. This is when it comes to the hard magnetic materials, you can see here in the graph it is having a large hysteresis loop, because of which they retain a considerable amount of their magnetic energy after the external field is switched off. So the properties of the hard magnetic materials are high remnant magnetization, high coercivity, high saturation flux density, low initial permeability, high hysteresis energy loss, high permeability. Examples are iron, nickel and aluminum alloys with certain amount of cobalt called alnico alloy. So the applications of the hard magnetic materials included, they used in the permanent magnets, magnetic detectors, microphones, flux meters, voltage regulators, damping devices and magnetic separators. So these are called the soft magnetic materials, or those for which the hysteresis loops enclose very small area. They are the magnetic materials which cannot be permanently magnetized. You can see here from the hard and the soft magnetic material, the first difference you should observe is the area of the hysteresis loop is large in hard magnetic materials. When it comes to the soft magnetic materials, the area of the hysteresis loop, that is the area under the BH curve, is very low. With that type of material is nothing but the soft magnetic material. The properties of the soft magnetic material includes low remnant magnetization, low coercivity, low hysteresis energy loss, and high permeability and susceptibility. The examples are permanent alloys, alloys of ferrous and nickel are the best examples for the soft magnetic materials. The applications for the soft magnetic materials includes in the machinery of transformer cores, microwave oscillators and matrix storage of computers. The applications of the magnetic materials, there are a wide range of applications, but we have included a few applications of the magnetic materials. When it comes to the key applications are power and electrical applications, data storage and information technology, medical and biological applications, industrial and consumer applications. These are the main applications, key applications for the magnetic materials. So that is how we have studied magnetic materials. Next one is dielectric materials. What exactly the dielectric material means? All the dielectrics are insulators, but all insulators are not, need not to be dielectrics. So what is actually dielectric material? Dielectric materials are the materials having electric dipole moment permanently. These materials are known as dielectric materials. A dipole is nothing but an entity which have equal positive and negative charges are separated by a small distance is nothing but dipole moment. So the dipole moment is the product of the magnitude of either of the charges, and separation distance between them is nothing but dipole moment. All dielectrics are electrical insulators and they are mainly used to store electrical energy. The best example is glass, plastic, water and polar molecules. Dielectric polarization. What do you mean by dielectric polarization? Means it occurs when a dipole moment is formed in an insulating material because of an externally applied electric field. When a current interacts with a dielectric or insulating material, it will respond with a shift in charge distribution. We can see here with the positive and negative charges aligned within the electric field and the negative charges aligning against it. This is the unpolarized material. This is the polarized material by an applied electric field. Dielectric polarizability. The ability of a dielectric material to get polarized is nothing but dielectric polarizability. The induced dipole moment is proportional to the intensity of the electric field. Polarization vector. The dipole moment per unit volume is nothing but polarization vector, that is denoted by capital P. Electric flux density is defined as a charge per unit area and it has the same units of dielectric polarization. D is equals to epsilon E and D is equals to epsilon naught E. So when we it as a polarization measures the additional flux density arising from the presence of material, we can see here D is equals to epsilon naught E plus P, which is an important relation between displacement vector and electric flux density. And again, dielectric susceptibility. The polarization vector P is proportional to the total electric flux density is and the direction of electric field. Therefore, the polarization vector can be written as epsilon naught psi E into E, where epsilon E is equals to sigma R minus 1. Dielectric constant. It is a ratio between the permittivity of the medium to the permittivity of the free space. It is denoted by epsilon R is equals to epsilon by epsilon naught, where epsilon is the permittivity in the medium, where epsilon naught is the permittivity of the free space. The electric displacement vector D quantifies the total electric flux density in a dielectric material, accounting for both free charges and bound charges. So its formula D is equals to epsilon naught E plus P. You can see here the displacement vector simplifies calculations in dielectrics by focusing on the effect of its free charges, making it crucial tool in electromagnetism, where D is equals to epsilon naught E plus P, where D is the electric displacement vector, epsilon naught is the permittivity of free space and E is the net electric field vector inside the material. The polarization vector which describes the density of dipole moments. So the relation between electric vectors we can see here. In the dielectric, the electric displacement vector D is related to the electric field vector E and the polarization vector P by the equation D is equals to epsilon naught E plus P. Understanding these vectors, we can see we have interrupted D is equals to epsilon naught E term represents the effects of the free effect of the free charges that would exist if the material were a vacuum. D is equals to P. This term represents the effects of the bound charges that are induced in the dielectric material. Therefore, the electric displacement vector D provides a comprehensive way to describe the dielectric behavior in a dielectric medium by accounting for both the external field in the material's medium response. These are the types of polarization. There are 4 types of polarization. One is electronic polarization, one is ionic polarization, orientational polarization, space charge polarization. So, first one we will I would like to study is electronic polarization. When an electric field is applied on a dielectric material, then all the positive charged nucleus displaces in the direction of field and all the negative electron clouds of atoms move in positive direction. This kind of displacement will produce an electric dipole within the atom, that is dipole moment is proportional to the magnitude of field strength is given by mu is directly proportional to E. Mu E is equals to alpha E into E, where alpha E is the electronic polarizability constant. Alpha E is equals to 4 pi epsilon naught into R cube. Hence, electronic polarizability is directly proportional to the cube of the radius of the atom. Next one is ionic polarization. The ionic polarization due to the displacement of anions and cations in opposite direction and occurs in ionic material when placed in an external electric field. When atom forms molecules, and it is mainly due to the relative displacement of the atomic components of the molecule in the presence of an electric field. As you can see here, mu ionic is equals to E square E by W naught square by into 1 by small m into plus 1 by capital M. Thus, we can say the ionic polarizability alpha I is inversely proportional to the square of the natural frequency of the ionic molecules and its reduced mass, which is equivalent to 1 by m plus 1 by capital M. You can see this is the figure where we can see displacement of anions and cations in the opposite directions. Next one is orientational polarization. It is also called as dipolar or molecular polarization. All the molecular dipoles are oriented randomly when there is no electric field. In the presence of electric field, all these dipoles orient themselves in the direction of field. As a result of net dipole moment becomes enormous. P naught is equals to n into alpha naught into E, where alpha naught is the orientational polarizability constant, which is mu square by 3 kt. That is how we can determine the total polarization is the summation of electronic polarization, ionic polarization and orientational polarization. You can see the formula here. Alpha is equals to alpha electronic plus alpha ionic plus alpha orientational. We will get 4 pi epsilon naught r cube plus E square by W naught square into 1 by M plus 1 by capital M in plus mu orientational square by 3 kt, which is this is known as Langevin-Debye equation for total polarizability in dielectrics. Next one is internal fields or local fields. The total field acting on an atom inside the polar dielectrics is nothing but internal field or local field. It is also known as Lorentz field. How this internal field is evaluated means, consider a dielectric can be placed between the plates of a parallel plate capacitor and let there be an imaginary spherical cavity around the atom inside the dielectric. That is how we can see here. We have 4 internal components, E1, E2, E3, E4. You can see here, this is the dielectric material and this is a spherical cavity. This is the electric field is applied along the axis. So the field E1 is the field intensity at A due to the charge density on the plates is denoted by E1 is equals to E plus P by epsilon naught, and field E2 is the field intensity at A due to the charge density induced on the two sides of the dielectrics. E2 is equals to minus P by epsilon naught, and E3 is the field intensity at A due to atoms contained in the cavity. We are assuming as a cubic structure. E3 is equals to 0. This field E4 is due to the polarized charges on the surface of the spherical cavity. We can see dA is equals to 2 pi r square into sin theta into d theta. The E4 is denoted by 1 by 4 pi epsilon naught dq by r square. So dE4 is equals to P by 2 epsilon naught into cos square theta into sin theta d theta. Now after getting E4 is equals to P by 3 epsilon naught, the total internal field or Lorentz field or local field is denoted by EI, which is the summation of 4 internal fields E1, E2, E3, E4. We will get EI is equals to E plus P by 3 epsilon naught. As you can see here, this is the total field acting on an atom inside the polar dielectrics is nothing but local field or Lorentz field or internal field, which is denoted by EI is equals to E plus P by 3 epsilon naught. Next one is classes-Mossotto relation, which is very important relation, especially in dielectrics. The relation between dielectric constant and the polarizability of a dielectric is nothing but Clausius-Mossotto equation. The relation between dielectric constant and the polarizability of a dielectric material is nothing but Clausius-Mossotto equation. The induced displacement is directly proportional to the local field. Consider a dielectric material having a cubic structure and assume ionic polarizability and orientational polarizability is 0. Alpha I is equals to alpha naught is equals to 0, where EI is equals to E plus P by 3 epsilon naught. So after doing all the derivation, we will get the Clausius-Mossotto relation. N alpha naught by 3 epsilon naught is equals to epsilon r minus 1 by epsilon r plus 2. N alpha E by 3 epsilon naught is equals to epsilon r minus 1 by epsilon r plus 2, which is the Clausius-Mossotto equation. The relation between dielectric constant and the polarizability of the dielectric material is nothing but Clausius-Mossotto equation. Next one is frequency dependence of polarization. The frequency dependence of polarization in dielectrics arises because different polarization mechanisms, that is orientational polarization, electronic polarization, ionic polarization, orientational polarization, how these polarizations respond at different frequencies. So electronic polarization is fastest, followed by the ionic dipolar and orientation. And finally, the slowest space charge polarization. As the applied electric field frequency increases, slower polarization mechanisms can no longer keep up and drop out, leading to a decrease in the dielectric constant, which is known as permittivity, and a reduction in the total polarization response. You can see here alpha naught, alpha I, that is ionic polarization, orientational polarization, electronic polarization. When we plotted a graph between against frequency and polarization, how these three types of polarization is responding at different frequencies, that is microwave region, infrared region, and ultraviolet region. That is how we can study the frequency dependence of polarization in dielectric materials. So in this unit we have covered the magnetic materials from starting itself, and dielectric materials. In the magnetic materials we have studied the basic terminology and or origin of magnetic moment and classification of magnetic materials: dia, para, ferro, antiferro, and ferri. And then we have studied the domain concept of ferromagnetism, and then hysteresis curve, that is BH curve, and then differences between soft and hard magnetic materials, and then applications of magnetic materials. Thereafter, dielectric materials, classification of dielectric materials, and polarization, dielectric polarization, and then electric flux density, relations between electric flux density and displacement vectors. And we have studied the types of polarization: electronic, ionic, and orientational polarization. We have studied the internal field, local field, or nothing but Lorentz field. And then the most important relation in dielectric materials, Clausius-Mosotti relation, and then the frequency dependence of polarization. That is how we have covered the dielectric and magnetic materials. Thank you.